Hello and welcome to this course on electronics. My name is Emanuele Varelli and I will guide you through the material of this course. We can start our journey here with this very nice slide, which is there just to show you one very fundamental concept, which is what do we mean by nano. So as we can see here, there are so many different objects that go from centimeters down to nanometers and beyond to the angstrom. So by nano, what we mean is everything that is below 100 nanometers, actually between 100 nanometer and 1 nanometer. So the nanoscale, what we mean by nanoscale is actually something that has a size, a feature size that is between 100 nanometer and 1 nanometer or so. So this course is based on a 14-hour contact time, 2 hours per week, and we will be meeting during week 1 to 7. The exam is based on an assignment which will be both qualitative and quantitative. In few words, I can say that this course is actually a journey to explore the physics of the most fundamental electronic devices of our time, which is the transistor, the MOSFET, and the solid-state non-volatile memory, which is actually the flash, the floating gate. These devices have driven the most dramatic revolution in history, the micro-nano electronic revolution, and this is what we will talk about. So we will also explore the challenges related with scaling into the nanoscale, as well as new approaches ahead for both these devices. Regarding the books that you can have a look at, the fundamental one I would say that you could look at is Z, Physics of Semiconductor Devices. You can find it in the library, and there are also some e-books that are available through our library, and these are listed here. Very nice books. We don't do everything obviously that is in there. I just picked some things that are quite interesting, and please look at the reference marks that I put at the bottom of some of the slides that could point you to the reference I've used to create that particular slide or that particular content. Now, on this slide, just a few more details about the course. So what I'm expecting you to learn, and what you should try to do in order to do well in this course. So please read this through and try to stay tuned and follow what we do as much as you can. Obviously, ask anything you may want to ask. You're most welcome, obviously. Okay, this is the content of the course. The course is actually divided in 8 big chapters, if you like. At the beginning, we will talk about Moore's law, what it is, what it means, what is happening, and so on and so forth. Chapter 2 is in a way a sort of a recap for you of concepts that maybe you've come across during the last few years. So we talk about general materials, metals, dielectric, and semiconductors. Chapter 3 is deals with what it means nanoscale physics. So and specifically having a look at some of the things that we will need for our devices. So we will talk about potential wells, barriers, transfer matrix, resonant tunneling, quantum confinement, Coulomb blockade, and quantum of conductance. And chapter 4 is also in a way a recap of some concepts. We talk about two-terminal devices, so p-n junction, metal semiconductor interfaces, and MOS devices, metal oxide semiconductor devices. So some of these things, I believe, especially the PN junction, is something that some of you may have come across during the previous years of your studies. So don't worry about this, but it's good to revise some of the concepts. Chapter 5 is actually about conduction mechanisms, so probably this is something new for you. So we will discuss the several types of conduction mechanisms that you could have in a material. Now there are two types of conduction mechanisms that two groups maybe, electrode limited, and we will look at direct tunneling, Fuller-Nordheim tunneling, tunneling assisted, trap assisted tunneling, Schottky barriers, and bulk limited mechanisms, which are ohmic, hopping, and Pull-Frankel. So obviously it is interesting for us to see these mechanisms because they are obviously nanoscale phenomena, and so they are important for understanding generally how electronic devices work in the nanoscale. Chapter 6 is a very brief look at how fabrication of this sort of devices is made. And chapter 7 and 8 are actually two big chapters that actually deal with the devices that we mentioned before, so transistors and solid-state non-volatile memories. So we will have a look at in depth. We'll spend quite some time on these two chapters, as you will see. Let's start now with chapter 1, where we will discuss in detail what we mean by the micro-nano electronic revolution. In the first half of the 20th century, the fundamental component that we used in advanced electronic devices was the vacuum tube, or also called simply the valve. And the reason it was so important is that it was the most fundamental nonlinear electronic element, as it was based on thermionic emission, its nonlinearity in its electronic behavior. And because of this nonlinearity, it was used in groundbreaking inventions, like one of the most important ones that we should mention is obviously the electronic amplifier. Okay, and it is worth mentioning here that still today there is a large number of amateurs that use valve-based electronic amplifiers to, for example, listen to music, as they believe that provide a better quality of sound. There was, though, big problems that came together with this nice device, and the main one is that the vacuum tube has very little limited scalability, and also that the vacuum required inside the tube had limited durability. The weight was also a problem, and especially the power consumption. It was a hugely power-hungry device. You can see some of these devices here. So in this nice image. Everything changes though in 1947 with the invention of the transistor, which stems the beginning of the solid-state era. So the transistor was the first three-terminal device that was all made with solid-state elements, so just a chip of material, if you like, and it was basically the element on which all integrated circuits would have been made of from that point onward. And this marked effectively the start of this microelectronic revolution. So there was a lot of interest, of course, on this new technology because it had the potential to be extremely scalable and especially low power. The transistor that was invented in 1947 drove to a Nobel Prize in 1956 to their inventors, as we see here in the image in the bottom right here. A brief timeline of the advent of this the semiconductor era. So we said in 1947 we have the first transistor, which was actually the BJT transistor. BJT stands for bipolar junction transistor. In 1958 we have the first actual integrated circuit, which you can see here on the top right image. And 1959 we have the first planar transistor. So this is a completely new concept, is the MOSFET transistor, and that's basically what we will discuss later on in this course. And 1965 the first operational amplifier, and then 71 the first microprocessor, and so on and so forth. And then it's a story that more or less we know how it goes. Okay, so we've said that in this course we will one of the fundamental devices is actually the transistor. The fundamental device that is behind the microelectronic revolution is actually the MOSFET transistor. And diagram of this device is represented here on this slide, and is made of, it's a three-terminal device. So we have three contacts, which is the source, the gate, and the drain. And but the reason I'm showing you this slide is that actually to see how a transistor is actually made of, what it is made of, and actually the materials it is made of. So we have, for the three terminals, we have metals, so we have conductors, and then we can see that below the gate we have an oxide that is effectively an insulator. And then between the source and the drain we have what we call the channel of the transistor, and this whole block of material here is actually a semiconductor. So in order to understand how these electronic devices work, we actually have to get a good understanding of how conductors, insulators, and semiconductors actually work. And that's why in chapter 2 we will have we will revise these concepts. Okay, let us now have a look at Moore's law. So what is this law about? Well, Gordon Moore, the guy in the picture here, at the time, 1965, he was the director of the research and development facility Fairchild Semiconductors, and he wrote a paper where he was actually showing that came to realize that the number of components per chip doubles every year. So this is what we call the Moore's law. It doesn't matter the chip or whatever you're dealing with. What is true, and that's what he realized, is that the number of components per chip doubles every year. In this was a really groundbreaking paper, because in this paper he also discussed reliability issues, yield, cost, power density, heat dissipation, and so on and so forth. So it was at the time it was a really a groundbreaking paper in the microelectronic field, especially at a time when microelectronics was still at its beginnings, and there were still a lot of skeptics about, you know, this idea of using microelectronic circuits and so on and so forth, rather than the other approach that was still being used, using, you know, based on vacuum valves and so on. So most importantly, his paper was making a prediction, and the prediction was that in 1975 we would have around 65,000 transistors per chip. And the funny thing that made of is the reason of why he's so famous, and this prediction is actually today remarked as Moore's law, is that he was right. So in 1975, indeed, the growth in the field was such that indeed we had 65,000 transistors per chip at the time. In 1975, then his Moore's law was then revised, and it was actually adjusted to a doubling, from a doubling every 1 year to a doubling every 2 years. And the reasoning from Moore is that there are mainly three factors that contributed to the scaling that they had observed. So the first one is decreasing component size, the second one is increasing chip area, and the third one is device cleverness. Device cleverness refers to how much the engineers could reduce the unused area between transistors. And the point made by Moore at the time was that this third point was being in a way lost, because there was no more cleverness to put too much into the device design. So in the future, the scaling of his scaling law was going to be mainly driven by point 1 and point 2 here above, and this was basically the reason why there was this less aggressive, let's say, scaling from doubling every 1 year to doubling every 2 years. Actually, different technologies scaled at different pace, as we can see from the next slide, where actually logic chips or microprocessors would scale at a doubling every 2 years, while memory chips would scale at just a slightly faster rate, doubling every 18 months. And this is due to the fact that memory chips are just a bit simpler than microprocessor chips. Now, of these three technology drivers that were identified by Moore, one is really special, and this is the decreasing of the dimension of the transistor. So shrinking the size of the transistor is actually really special. And the reason is that for quite a while, for several decades actually, shrinking the transistor offered something that never happens really in the world of engineering. There were no trade-offs. So shrinking a transistor simply meant making everything better, and basically meant that every successive transistor generation was better than the last. So this is in a way also emphasized by these Dernard's MOSFET scaling rules. If you call lambda the scaling factor, which means basically that the device dimension goes down as 1 over lambda, then we can see that we can, by the same factor lambda, we decrease the voltage, decrease the current, decrease the capacitance, decrease the delay time, because the objects are smaller, so obviously there is less time needed for signals to propagate. We also decrease the transistor power. But we can see though that the power density remains the same. So this is a point that we will pick up again a bit in a moment. So this was quite an amazing situation where by shrinking the size of these devices you could get things to work actually better. The transistor would use less power, much less power actually, would work at a lower voltage, and there would be less delay time, which means that the actual microprocessor would work in the end at a faster frequency. Okay. It's worth mentioning that Denner's scaling rules are based on the assumption that we keep basically the electric field to operate a device constant. So while we go from this device to this device that is obviously smaller, what we are assuming here is that to operate this device we keep the electric fields, generally the electric fields, constant everywhere. So since the electric field is given by the voltage applied across 2 points and the distance between these 2 points, by shrinking the distance we need to reduce the voltage as well to keep the electric field the same. And so that's why all these scaling rules that are reported here go the way they go. Okay, so the voltage decreases and so on and so forth. So this situation is in a way represented by this virtuous circle of the semiconductor industry. So from transistor scaling we have better performance and lower cost. So this drives the market growth, which drives better investments in the industry, and so on and so forth. So this is a phenomenal situation here that we've been through for several decades. On this slide we can actually see how the shrinking took place during the years. So we can see here the channel length, for if you remember, if we go back to the slide where we showed the transistor, the channel length is actually this distance here between source and drain contacts. So in this graph we are plotting the channel length of the transistor being manufactured versus the year they were manufactured. So we can actually see that we go from up here around 5 microns down to in the year 2010 down to 32 nanometers, for example. So these red dots are actually the years when this specific channel length actually appeared for the first time. Oh, by the way, all these the channel lengths that are shown here are actually also called technology nodes. So for example, 32 nanometer is one technology node, 45 nanometer is another technology node, 65 is another technology node, and so on and so forth. So the advancement of the technology goes in steps that are somehow discrete, if you like. We will come to this point maybe later in the course, in these slides. Okay, by shrinking though the size of the transistors and of the devices, and so cramming more and more devices into a chip, what actually caused is that the power density in the chip skyrocketed pretty quickly. So we can see here on this slide that the power density of microprocessors really around after the 90s, after the 80s, started to really go up quite rapidly. And obviously this is really a dangerous situation. So this is really the first of the problems that we start to see when you start to shrink the devices and put more and more devices into a chip. But there are more problems, and one of these problems is that you start having leakage currents. So a transistor is actually can be used, and mostly is used as a switch. So the transistor can be put in the on condition when it conducts current, if you like, and can be put in the off condition when it doesn't conduct. And this is done by operating on the gate. So when it is on, the transistor will consume a certain active power, which on this plot on the left is represented by these blue dots. When it is off, ideally it should consume zero. But because of leaks and tiny defects anyway that are always there, there is always some current that leaks through the channel, and so there is some power consumption even when the device is off. This is denoted by this subthreshold power density. We will come to these terms. We will understand what they mean later on during when we will deal with chapter 7. But nevertheless, we can very simply understand this concept. When it's on, it's consuming obviously what it has to consume. When it's off, should be zero, but is not really because of these defects. So it is consuming a little bit. Now, what happens is that as you shrink the device, you have to shrink everything. You shrink the channel, you shrink also the gate oxide. And so this drives to leaks that can go through the gate oxide, can go through the channel, and so overall, as you shrink the device, so here the gate length is decreased, and so imagine that if we start shrinking the device, we are moving in this direction on this axis. At the same time, the subthreshold power goes up. That's what is happening. So we move along this path. And so what happens basically is that there will be a moment when you shrink too much that basically what you consume when the device is on and when the device is off is basically the same. And this is obviously the moment where we will be in big troubles. And here we can actually see from a different point of view a similar in a similar way what we just described. So this is actually the power consumed by a device in active mode and due to leakage. So basically when it's off the device. And so here also we can see that it is just after year 2000 that we have reached the problem, the moment when we have a problem. So we will see what to do, what we will do, or what people have done maybe. So on this slide there is also another of the actual issues that people have come across during the scaling process, and this is that it deals with the actual voltage applied in the devices. So again, these dots here show the early adopters of that specific voltage. So we can see that as we shrink the device, as we decrease the channel length, the actual voltage applied to the transistors was actually decreasing. This is the the best, let's say, that we could find in the market. But in reality, the mean existing across the market is actually given by this green curve. And we can see that in reality, since, while there's been a decrease in the actual voltage applied for few generations, but after, the technology node 130 and beyond, basically the voltage applied is more or less there, is not really changing a lot. And the reason is that there are technical problems in decreasing too much the voltage that we have to deal with, mainly noise, electrical noise, obviously. So all these problems that we've briefly discussed that go with shrinking the size of these devices meant that basically in the last few years we've seen a dramatic rise in design costs to make these devices. Okay, and this is to overcome all these problems. So people had to really to work out solutions, how to solve all the problems we've seen. We will see what they've done. As we said at the beginning, with Moore's law, we were initially in a fantastic situation where there are no trade-offs. The more you shrink, the better it is. But now we are reaching slowly a situation where shrinking is becoming more and more problematic. And some companies are starting to see the effects of this. So we can see here in the top graph that indeed there are already companies where the cost per chip is actually starting to stabilize. It's not going anymore down, but is starting now to stabilize. On the other hand, there are other companies where things are still working. So Moore's law is still, let's say, alive, if you like. So, are we at the end of Moore's law? Well, we've highlighted some problems already. We can point them out better here in this list as 6 major issues. So the first one is related to scaling the feature size itself. So we are now reaching the scaling limits due to the finite size of atom, as simple as that. So the current state of the art is at now 14 nanometer, and obviously we should remember that in a silicon crystal, the nearest neighbor distance is around 0.2 nanometer. So this means that in the channel of a transistor made at this technology node of 14 nanometer, there are actually 14 divided by 0.2 atoms, which is 70 atoms, which is quite a small number, obviously. The other problem is related to power density, as we have said previously. So this has increased worryingly over the last decade, and so high power density causes malfunction, failure of device due to induced high temperatures. Another big problem, which is related to the previous one, is obviously heat dissipation. So as we cram more and more devices into a chip, the devices are more close to one another, so it becomes more and more difficult to actually remove that heat that is generated due to the difficulty in accessing actually the devices. So this obviously, this is a problem because, as again, this causes high temperatures, which cause failures. The other problem is, as we briefly said previously, is leakage current. So as we shrink, we have to shrink everything. We have to shrink the channel of the transistor, we have to shrink the gate oxide, and so all these processes cause an increase in the leakage current, which means an increase in the standby power of our devices. And this is particularly bad, especially for the development of low power devices, like the devices that are required for the development of mobile technologies. For example, tablets, laptops, smartphones, etc. The other big problem is, as we said, the supply voltage. So this has not been decreasing as much as we wanted, really. And so this also is a problem for low power devices. And finally, the cost per transistor. So this also has been decreasing for decades and was one of the major, basically, drivers behind, the success story of the semiconductor industry. But now is facing increasing difficulties due to the increasing costs, for example, in design and so on. So in trying to answer the question, are we at the end of Moore's law? Well, and having listed maybe all those problems, well, the answer really is no. It's not the end of Moore's law, but it's actually the transformation of Moore's law into something more. So we have actually, since people realized long ago now, during the 90s mostly, since people realized that Moore's law was going to get into some troubles, people realized that they could move in three possible directions. The one was called Moore, the other one more than Moore, and the other one is beyond Moore or beyond CMOS. So these three directions, if you like, could be shown on this type of diagram here, where we see that Moore means trying to keep effectively scaling alive in a clever way. We will see in a moment. More than Moore, on the other hand, is actually to diversify the technology. We will see that also in a moment. And beyond CMOS or beyond Moore is actually doing something completely new. So we can have a look at these concepts here in the next few slides. For example, Moore means trying to keep Moore's law alive, to further develop CMOS technologies using new materials and new designs. So using clever ideas. For example, one was to, for example, replace low dielectric constant dielectric materials. People have always been using silicon dioxide, for example, which has a low dielectric constant, and replace it now with high K materials. We will see that doing this effectively you can reduce the leakage currents. And the other was, for example, to instead of using silicon, use new semiconductor materials, for example, germanium or group 3 and 4 materials, or even abandon the idea of a planar transistor. So the planar transistor we've seen at the beginning of this course, this chapter, was actually this one. So this is a planar configuration where the channel is in plane here, and move to a 3D configuration like this one, like the FinFET, where the body of the transistor, which is basically this part here, the body of the transistor is actually a fin, and the gate is around it. Or move even to the gate all around concept, where actually the body is actually surrounded by the gate. So this nice represented in this nice diagram here. So progress basically will now be made via innovation and not just by scaling. So that's the idea of Moore. So be clever. So try to change some things to keep Moore's law alive. And in this direction, we can see how this was done and has been done in the last few years by looking at this slide, where we show which materials we used in the microelectronic field in the 1980s, which are these blue elements here. In the 90s, we started using a few more elements, but in the year 2000 and on, we've actually been using a lot more materials, and that's because of Moore. So this drive to keep Moore's law alive. Okay, now regarding More than Moore, what is More than Moore? Well, so More than Moore is actually looking at the other facet of microelectronic products, complementing the digital part of an integrated system. So it's actually an approach that allows for non-digital functionality of a product that do not necessarily scale according to Moore's law, but provide additional value in several different ways. So this, for example, these More than Moore devices, for example, provide conversion of non-digital as well non-electronic information, for example, mechanical, thermal, acoustic, chemical, optical, biomedical, to digital data and vice versa. So most of these are, for example, sensors or devices for energy scavenging, or and so on and so forth. So all those listed there. So really, in the More than Moore approach, there is a new virtuous cycle for the semiconductor industry. It's not anymore the one that we know of, but there is a new one, which is this one here, where technology, devices, circuits are provided with increased functionality and or lower cost. This then drives market growth, which drives then investment, and so innovations in technology, and so on and so forth. And finally, beyond Moore or beyond CMOS. Well, this is really the nanoelectronics era. So significant breakthroughs should be expected in the long term from the progress in the nanometer-sized functions. So beyond Moore is actually all about doing electronics using new state variables. So instead of using charge, which is basically what we've been using until now in order to operate transistors and all the other devices that have been part of the microelectronics field, we should use now other state variables, for example, spin. So we have spintronics that has been developed, molecular state, phonons, the mechanical state, resistance, and so on and so forth. So examples of devices that are going in this direction: resistive memories, new type of memory technology, spintronics, molecular electronics, and so on and so forth. So obviously the problem with this technology is that most of these technologies impose very profound changes in the industry, as we can understand. The current industry is focused and based on silicon. So we should remind, though, that most of this technology impose very profound changes in the industry, because the industry is currently based on silicon, and so all these technology require that we switch from silicon to completely something else, completely different. Okay, this is the end of this chapter, and we will continue next time with chapter 2. Thank you. Bye.